our group today are going to explain about coordination compound. We are going to discuss more detail about complex ion. But first of all, let me introduce my team members. My team member is Anissa Dahia binti Sarji, Khadijah Farhana binti Mama Yusra, Nur Daniel Shazwina binti Mama Azwan, and me myself Nur Hanisa Safia binti Nur Hafizah. This is our table of contents, what we are going to explain to you guys. First, we got objectives, introduction, finding and discussion, application, and conclusion. Without wasting any more time, let's get started.
The objective of the experiment is to understand and identify which part of the compound to name first, to learn the visual difference between the metal, ligands, and counterions, and lastly, to name simple complexes through step by step.
Hi, my name is Khadijah, and in this video we're going to discuss about coordination compound. Coordination compounds are chemical compounds that consist of a central metal, atom or ion surrounded by other molecules or ions called ligands. These ligands are attached to the metal through coordinate covalent bonds. The central metal is usually a transition metal. It acts as an electron acceptor by receiving electron pairs from the ligands. Ligands are molecules or ions such as water H2O, ammonia, and H3 or chloride Cl-. They donate the electron pairs to the central metal to form stable complexes. The coordination number refers to the number of ligands directly bonded to the central metal ion in a coordination compound. Coordination compounds are very important in a daily life. They are used in medicines such as anti-cancer drug, in industry for making dyes and pigment, and as catalysts to speed up chemical reactions.
Let's discuss how we systematically name coordination compounds. There are 5 key rules to keep in mind. First, we always name the cation before the anion. Within the coordination complex itself, the ligands are named before the metal. We list this ligand in alphabetical order regardless of their charge. To finish the name, we must indicate the oxidation state of the metal using Roman numerals in bracket. Finally, remember that the name of the complex ion is always written as one single word. Let's look at the example on the right figure to see this in action. First, we have CONH3 6Cl3. This is called hexaamine cobalt 3 chloride. And next we have FeCN6 4-. This anion is the hexacyanidoferrate 3 2 ion. To name a complex ion, we follow a consistent sequence. Start with the prefix and add the ligand name, followed by the metal name, and finally the oxidation state in parentheses. This creates a single continuous word for the complex part. Let's apply this to our first example for cobalt complex. First is CONH3 6Cl3. We have 6 amine ligands, so the prefix is hexa plus amine. The metal is cobalt with an oxidation state of 3. Combined with the counter ion, the full name is going to be hexaamine cobalt 3 chloride. Our second example is platinum complex, PTNH3 2Cl2. Here, we have 2 amines and 2 chloridos. Following the alphabetical order, it becomes diamine plus dichlorido. It is listed as dichloro, but the modern IUPAC recommendation is dichlorido. We add the metal platinum and the oxidation state 2. So the result is diamine dichlorido platinum 2.
So moving on, we will discuss the compounds that surround the central metal ions known as ligands. Ligands are ion or molecule that bind to a metal ion by donating a pair of electrons and therefore act as Lewis bases. So we classify them based on their density and how many atoms they use to bind. So for the first one, unidentate ligands such as water or ammonia use a single donate atom. Bidentate ligands such as ethylene diamine and use 2, and polydentate ligands such as diethyltriamine use more than 2. And as you can see in the table of ligand in the slide, we distinguish them by their charge and IUPAC names. For example, neutral ligands like ammonia and water are named amine and aqua, while ionic ligands like bromide or chloride change their endings to bromido and chlorido. Notice that some neutral ligands are special exceptions to the standard molecule naming rule. After identifying the ligand type, the next step is indicating the number of each ligand present in the complex. This is then using prefixes which is differ depending on the complexity of ligand's name. For simple ligands such as amine of aqua, standard Greek prefixes are used including G, 3, and tetra. However, the complex ligands, particularly polydentate ligands or those that already contain a prefix, the prefixes bis, tris, and tetrikis are used. For instance, instead of diethylene diamine, the correct form is bis ethylene diamine. And for bidentate, there is 2 oxalates. We say them as bis oxalates instead of 2 oxalates, which also presents 2. There's also a name that already has a prefix in it, such as triphenylphosphine. So when naming complexes with more than one type of ligands, ligands are listed in alphabetical order. It is important to note that prefixes are ignored when determining this order. The final component in naming a coordination compound is determining the oxidation state of the central metal ions. A According to IUPAC convention, the oxidation state is written in Roman numerals in parentheses at the end of the complex name. To determine the oxidation state, the total charge of the metal ion and all ligands must equal the overall charge of the complex. For example, in a neutral platinum complex, the overall charge is 0. Since ammonia is a neutral ligand and each chloride ligand carries a -1 charge, the oxidation state of platinum is calculated to be +2, written as 2. In contrast, for an anionic complex such as the ferrite ion with an overall charge of -3, the 6 candidate ligands contribute a total charge of -6. Therefore, the oxidation state of ion is +3, written as 3.
We will study about how to name the metal ion in a complex ion. Step 1. Find the oxidation state of the metal. Determine the overall charge of the complex. Identify ligand charge. If the charge is neutral, it will be 0. And if the charge is negative, it will be -1. And then you can calculate the metal oxidation number. Here I have provided the example you guys can see. Step 2. Name the metal based on complex charge. Positive or neutral complex, use the normal metal name. Write oxidation state in Roman numerals. Here also I provide the examples you guys can see. And if it's a negative complex, metal name ends with ATE, which is 8. Some metals use Latin names. As you guys can see, I provide the Latin names table, which is Fe will be a ferrate, Cu cuprate, Ag argentine, Sn stannite, Pb plumbate, Co cobaltite, Ni nickel. Step 3 is position of metal name. Metal name is written last, oxidation state in brackets. This is the format, ligands plus metal, which is their oxidation state. Examples of octahedral complexes you guys can see here. Next is suffix for anionic complexes. An ionic complex is a complex ion with an overall negative charge. When a complex is negative, the metal name ends with 8. The oxidation state of the metal is written in Roman numerals. Purpose of 8. To distinguish anionic complexes from neutral or cationic complex. To provide clarity and consistency in coordination compound naming. A key reminder, positive or neutral complex will be a normal metal name. For negative complex, metal name plus ATE. Synthesis of the name. Step 1. You need to identify overall charge. If the complex ion is negative, use 8. Step 2. Name ligands first. Use alphabetical order. Step 3. Name the metal last. Use 8 form. Apply Latin name if required. Step 4. Write metal oxidation state. Roman numerals in brackets. Here are the example we have provided to you guys.
Coordination chemistry isn't just theoretical, it is a cornerstone of modern medicine. Perhaps the most famous example is cisplatin, is a platinum-based complex used extensively in cancer therapy. It works by binding to DNA, preventing cancer cells from replicating. Additionally, for diagnostic, we use radiopharmaceuticals like technetium complexes. This allows doctors to use medical imaging to see inside the body with incredible precision. We also see this ion acting as antibacterial agents. Silver-based complexes such as silver sulfadiazine are essential in treating infections and are even being adapted to combat viral pathogen. In the food industry, complex ion play a vital role in both how our food looks and how it lasts. For instance, copper chlorophyllin is a common food colorant. Because it is a copper complex, it provides a more stable green hue than natural chlorophyll, while also acting as an antioxidant. This ensures that processed foods maintain an appealing natural look for longer periods without the use of harsh synthetic dyes. And finally, modified starches often involve complex ion like metal, citrates, or lactate. These complexes are used to precisely adjust the viscosity and gel strength of products. You will find this technology used heavily in the production of alcoholic and specialty beverages to ensure the texture remains consistent from the first sip to the last.
In conclusion, this video has explained the basic concept of coordination compounds by focusing on their main components, which are the central metal ion ligands and counter ions. Understanding this component is important because each part contributes to the overall structure of a coordination compound. This video also discusses which part of the compound should be named first by following the correct naming rules, by clearly identifying the central metal and distinguishing it from the ligands and counter ions. The naming process becomes more systematic and easier to understand. Additionally, the visual difference between these components were highlighted to improve recognition when observing chemical formulas by using a step-by-step approach. Simple coordination compound can be named correctly, providing a strong foundation for further study in coordination chemistry.